Okay, so we're going to start talking about some of my favorite material and maybe my most favorite material of the course, numerical integration based on interpolation. And this is going to get us into some cool stuff. So we're going to apply some of the stuff we learned back in polynomial interpolation. Talk about Lagrange polynomials. So define our Lagrange polynomial Li to be this product as we had it before. And then we would have that our P of x equal to the sum of I equals 0 to n of f of xi times Li of x interpolates the function f at the points x0 through xn. So we have this interpolating polynomial p. The idea is that p is close to f, so that when we take the integral of f, it'll be close to the integral of p. Now, we don't know what the heck f is, but we do know that p is a polynomial, and we can integrate polynomials. So we can just plop this down under the integral sign, and since it's a linear combination, we can take it out and we can get our approximate integral as the sum of my values f of xi times the integral of these polynomials on the interval from 0 to b, from a to b, okay? And so to put this in general terms, we'll talk about what's called a Newton-Cotes formula, which is that the integral of f of x dx is approximated by the sum of I equals 0 to n of ai f of xi. And here we're taking the ai is equal to the integral of this Lagrange polynomial, okay? So let's do an example, and one general example is the trapezoid rule. Okay, where we can have L of 0 is b minus x over b minus a. L1 of x is x minus a over b minus a. And we calculate our a's here, and they're both, our a1 and a0 are both equal to b minus a over 2. Plop that in, and we have a simple formula for integration right there. Okay, so the trapezoid rule, of course, gives us an approximation, and there will be an error in that approximation. We can take the absolute value of our integral minus our approximate integral, do our triangle inequality, apply a previous theorem we had back from polynomial interpolation, saying the difference between this function and its polynomial interpolation is equal to 1/2 f double prime of c times x minus a times x minus b for some c between a and b. And this product of x minus a, x minus y is going to be non-positive on the interval we're interested in. So when we integrate its absolute value, that's equal to the negative integral of this product, which is, okay, a quadratic function which we can integrate, which integrates exactly to this. And so our error is this right here. And so notice in particular, if our function was x or a constant function, if you take its derivative twice, it's 0. So this is saying the trapezoid rule is dead on accurate for constant functions and for linear functions. Okay. Now, and we can piece it together along intervals in a partition to get what's called the composite trapezoid rule, which I'm pretty sure you probably saw in Calculus 1. So we need not spend too much time on it here, because we're going to want to talk about something that's interesting, a bit more interesting, and it's going to ultimately be a bit more powerful. So in general, what we have is that we can approximate the integral of a function by a linear combination of its values on partition points or knots within the interval. Okay, and so let's say it like this. Let's say let's find these constants so that we get exact results on polynomial power, or excuse me, on integral powers of x up to x to the nth power. And so to make it clear what I mean, okay, let's suppose we have x0 equals 0, x1 equals 1/2, and xn equals 1. They're all in the interval from 0 to 1, okay? And we want to have an exact approximation for f of x equals x, f of x equals 1, f of x equals x, and f of x, and this should be an x squared, okay? Just imagine you've got the 2 there, all right? This function is supposed to be this function. All right, so if we take this expression here and plug in this constant function into it, we get this. If we plug this function into it, we get this. And if we plug the x squared function into it, we get this right here, right? We're just putting f here and f here, doing our evaluations. And so then we have 3 equations, 3 unknowns. We can solve it, and it has a solution. A0 is 1/6, A1 is 2/3, and A2 is 1/6. And so integral from 0 to 1 of f of x is equal to 1/6 of f of 0, 2/3 of f of 1/2, and 1/6 of f of 1. And so if we want to approximate, say, cosine of x, we evaluate these 3 points, and we get an answer which is accurate to 3 decimal places, okay? Now, if we'd had a quadratic function, it would have been dead on accurate, okay? But cosine, yeah, it's in spirit, it's like a polynomial, and so we get a really nice 3-digit approximation. Okay. So it also turns out that what we just did there is like Simpson's rule. Okay. And here is the error formula, and it's good. Okay. So I wanted to try out that method of undetermined coefficients we looked at. So what I did, we're going to do some NumPy. So I imported NumPy as NP. And then I created a function that will create a coefficient matrix for me. And I need a list of functions as my input and the knots as an input. And so this, you can study this if you want. It works, okay? And then I needed a solution vector, okay? So I did this, and notice I'm using np.matrix, I'm using np.nl, np.linalg.solve, okay? And then I'm define a function integrate. Well, this integrate function is just going to do the method of undetermined coefficients. I'm proud of this function. It's a very Pythonic function. Okay, and so I have my list of polynomials right here, the constant, the function x, and then the function x squared, and then my knots, again, this as we had in our slideshow. I get the coefficient matrix, okay. I then have the values, calculate the coefficients, and then I do my integration, and there it is. I get my approximation, okay. If I wanted to, say, integrate say lambda x goes to, say, x, let's do x cubed. It's a little bit big. And for the same knots and for the same coefficients, that'd give me, like, you know, almost exactly the correct answer, right? Just hardly worth arguing about.